welcome everyone. Thanks for coming. Just allow me to say a few words to introduce our speaker today. Our Lansdowne visitor is Professor Alex Rosa. He's a key figure in graph theory and combinatorics with expertise in graph decompositions and design theory. He obtained his PhD in 1966 at the Slovak Academy of Sciences under a student of Anton Kocik. And he took a permanent job shortly after that at McMaster University. Now Professor Emeritus there, has held numerous visiting appointments, for example at Waterloo, Rome, and Technion in Haifa. Professor Rosa has authored over 200 papers in graph theory and design theory, and his pioneering work at the interface of these two subjects remains central today. An example is the connection between graph labellings and decompositions, and that's the topic of Alex's talk today. In fact, an early paper on this topic was co-authored with Professor Rosa and the famous mathematician Paul Ehrlich. Nearly 50 years later, hundreds of researchers use these techniques, labellings, to construct decompositions, and this leads to some challenging and beautiful conjectures. Again, Alex will tell us more about that in a few moments. And at the same time, this topic has important applications to information-based sciences, including to error correction codes and management of network traffic, among many other things. So Professor Rosa was the recipient of the 2012 Euler Medal from the Institute of Combinatorics and its Applications for distinguished career contributions to combinatorics. He also received the Medal of Gerhard for merit in mathematical science in 2007. He's served on the editorial board of international journals and has had a number of special volumes and birthday conference in 2007 in Bratislava. It was my first time in Bratislava. It was great to be there, and there will be an 80th birthday conference for Alex this year in the Czech Republic. So I met Alex in '97. 20 years ago now, it's hard to believe, but so I was a master's student with Aaron Mendelson, who was a colleague of Alex. And we went to the seminar, Eric and I went to the seminar in Hamilton, and we were complaining afterward to Alex about a very difficult combinatorial design on 27 points. And I remember Alex said, essentially, I think it exists, and basically challenged me to find it on computer before he could find it by hand. And I considered this a terrifying challenge, and so about a week later, my hastily written computer program prevailed, but I owe all the success to the fear of Alex's challenge. Really led me to find that. So please join me in welcoming my friend and colleague, Alex Rosa.
Thank you very much, Peter, for the nice introduction. I have to start with saying, even though it sounds like a cliche, that I'm very glad to be in Victoria. I was trying to figure out how many times was I here at all, and I failed. I can't decide whether it was 6 times or 7 times. But I remember my first time, that was during the World Congress of Mathematicians in '74 in Vancouver, that I was here. And it's always a holiday for me, or how should I say it? It's a nice occasion to come here. And about a few weeks ago, actually it was in March, I got an invitation to contribute to a special issue of a journal. So this in itself is nothing extraordinary. I'm sure many of you get these invitations, especially with many new journals which are after your money with hefty paid charges. But what was interesting was the topic of both the journal of the special issue. The journal was called Health. And I'm a mathematician. I'm as far from health journals as can be. And the special issue was on rare diseases. Okay, But it didn't take me too long to figure out why I got this invitation, because I have written indeed about diseases, combinatorial diseases. And they must have done some search by computer and came up with this invitation. So I wasn't the first to talk about combinatorial diseases. I think Frank Harari was the first who, well, he talked about graphical diseases, foremost among them the four-color disease, and then later Derek Cornell and Ron Reed talked about graph isomorphism disease, and Kotzik, Sherlock Wang and myself talked about the labeling disease. So it's this labeling disease that I want to tell you a little bit about. Now, what makes for a good combinatorial disease? It has to be heavily contagious, so that you hear about it and you are hooked and you got sick with the disease. As far as cure for these diseases is concerned, as far as I can tell, only one of these diseases was successfully cured. That's the four-color disease, successfully but not quite satisfactorily, but it was cured. There are many people who are hooked on labeling disease. So where did it all start? Well, here is a picture of a nice medieval castle in Smolenice, what is today's Slovakia. It's a village. It's on a hill above a village. The village itself is located about 60 kilometers east of the capital city of Slovakia, Bratislava. It's a medieval castle, all right, but this incarnation that you see is more like end of 19th century, beginning of 20th century. And this castle belonged to Count Palffy, a very famous family of counts. But in 1945, after the war, this castle was nationalized, in other words, taken away. And in 1953, it became the property of the Slovak Academy of Sciences. And they use it till today for organizing conferences, but not only conferences, also weddings, recreational stays, and other things. And in 1963, this was the venue for the first truly large international conference on graph theory. Of course, large by standards of 1963 is not large by today's standards. Today, you get combinatorial conferences with hundreds of participants. At that time, the number of participants was between 40 and 50. But if you look at the list of participants, then you will see almost like who is who in graph theory at that time. Erdős, Galai, Sachs, Ringel, Michalski, Zykov, Kotzik, Fiedler, just to name a few people. They were all there. There were talks, of course, and there was a big problem session. There was a huge problem session, and a year later, a volume appeared from this conference. And here is one page from that volume. Now, I understand this is not readable, but this is a page which contains some problems. Among them, these two problems, which are prominent in that they both gave birth to combinatorial diseases, which are uncured till today. And there's one of them, problem number 25, formulated by Ringel, that I want to tell you about a little bit today. As far as the other problem is concerned, depending on time, if I have a time at the end, then I may say a few words about that one too. So, as I said, this is not probably readable, but in slightly different slightly different formulation, this is what became known as a Ringel's conjecture. The complete graph K2m plus 1 with 2m plus 1 vertices can be decomposed into 2m plus 1 subgraphs, each isomorphic to a given tree with n edges. So if somebody is not a graph theorist, still there are only two notions that one has to perhaps explain, and that's what is a complete graph. Well, complete graph with n vertices is a graph which has, not too surprisingly, n vertices, and any two are joined by an edge. Any two vertices are joined by an edge. And finally, there is also the notion of a tree. Now, tree is a graph which is connected and does not contain any cycles or circuits or whatever you would call them. So this is the formulation of a problem, and I think it's typical for problems of this kind that the formulation is very simple, easily understood, and in many cases these diseases arise in such a way that people think they'll cure it by the next morning, but it's not how it works. And here we are 54 years later, and the problem is still open. So how to approach a problem like that? Well, turns out that labellings, graph labellings of a certain kind, are the possible means of attacking the problem, this disease. What is a graceful labeling of a graph? This is another definition which is not difficult at all. So we have a graph with n edges. The number n is the number of edges. And now we are going to label the vertices of the graph with numbers from 1 to n in a manner that different vertices get different numbers. And the requirement is that if you look at the values of edges, which are obtained as an absolute value of the difference of the labels of an edge. So if you have an edge with the two vertices, the value or label of the edge is the absolute value of the difference of the two labels that you have there. And then you want the edge labels to be all different. And because there are n edges and n labels, so that means that all the numbers from 1 to n will appear. So that's the definition of the graceful labeling. But in fact, graceful labeling is one of the 4 labelings in a hierarchy, which I want to explain. Now, we have n, going back, we have n edges, and we have up to n plus 1 available labels for vertices. Now, what if the graph has more than n plus 1 vertices? Well, can there be such a case? Yes. There should have been one more panel, but I put it here on the blackboard. Here is a graph which has only 4 edges and 6 vertices, which means it cannot be labeled. Such a graph cannot be labeled. So we have a hierarchy of labelings: alpha labeling, beta labeling, sigma labeling, and rho labeling. Beta labeling is the labeling which is known as graceful labeling. The word or term graceful labeling is due to Solomon Golomb. So what is an alpha labeling? Well, it's a graceful labeling, but we have an extra added property that if you have a label, if you have an edge, and edge label, the two edge labels are, say, f of u and f of v, then one of them must be less than a certain fixed number k, and the other is greater than k. The other two labelings are weaker than graceful labeling. It's very similar, it's similarly defined, but now we can use the numbers not from 0 to n only, but from 0 to 2n. And finally, rho labeling is such that the labels, the edge labels, don't have to be from 0 to from 1 to n, but they can be instead of I, you can have the complement of I to 2n plus 1. So 2n plus 1 minus I. Let's illustrate these notions on some very simple examples. So here we have a tree which is called a path. And it is a path, right? This path has here 6 edges. Now, if we have a tree, I should have mentioned that if we have a tree which has n edges, then it will have exactly n plus 1 vertices. And that means that in a graceful labeling, we have to use all the labels from 0, 1 up to n plus 1 labels. So here we have 6 edges. We have to use labels from 0 to through 1, 2, up to 6. And they are used here. And we can see that it's a very simple rule how to gracefully label a path. So we start with the smallest label, then largest label, then second smallest, second largest, third smallest, third largest, and so on. So that shows that paths can always be gracefully labeled, no matter what its length. Now this tree is a so-called caterpillar. What is a caterpillar? Caterpillar is a tree which, when you delete its vertices of degree 1, its end vertices or leaves or whatever the name is, you are left with the path. Indeed, if you delete these edges which are incident with the vertex of degree 1, with only one vertex, then you are left with the path from what is labeled 21, 3, 17, 6, 12. The rule for labeling gracefully a caterpillar is very similar to the rule for labeling gracefully a path. You start at the beginning with the smallest labels, then you use the largest, second smallest, and so on. Tree is a bipartite graph. Any tree is a bipartite graph, so we can color the vertices with 2 colors, say black and white, so that every edge has 1 black and 1 white vertex. And the, say, white vertices are labeled with the smaller numbers and white vertices with the larger numbers. Here is another tree. Now that's not a caterpillar. Why? Because if we delete the 3 edges at the end, the 3 end edges, you are left with something which is not a path, it's a star. It's not a path. Well, this botanical terminology would not make too much sense to a botanist, because, or actually not botanist, but a zoologist, right? So this is caterpillar, and this is lobster. This is a graph this is a tree which is called lobster. What is a lobster? Well, a lobster is a graph which you delete the end vertices of that and then repeat the process, you get a path, okay? And let's look at the labeling of this, excuse me. Let's look at the labeling of this lobster. Actually, I have to say that this is not just a graceful labeling. Actually, it's an alpha labeling. And all the caterpillars have also labeling which are alpha labelings, the ones with the strongest property. This one, this labeling, which is graceful, you can verify that, right? We have, excuse me, we have all the integers from 0 to 6 appearing on a vertex, and edge labels are 6, 5, 4, 3, 2, 1. But this is not an alpha labeling. This is not an alpha labeling, because what would be that number k that we are after? Well, it would be, perhaps it should be 3. Well, no, because then edge 1, 3 is violates that condition, that extra condition. Could it be 4? Again, no. So it is not an alpha labeling. And in fact, any lobster which has diameter 4 and is not a caterpillar, well, cannot have an alpha labeling. That's one result that can be proved. Okay. Once you define these labelings were defined not just for trees, for any graph. So let's look at complete graphs, small complete graphs. Now here is a complete graph on 3 vertices, and because we have here some cycles, not all labels from 0 to n, where n is the number of edges, not all labels are used. Here, for instance, 2 is missing, but it is a graceful labeling, right? Because we have values of edges are 1, 2, 3. What about here? There are 6 edges, but there are several numbers missing there. But let's see. Is this graceful? Yes. 0, 1 is 1. The label is 1. Here is 2. 4, 6 gives 2. 1, 4 gives 3. 0, 4 gives 4. 1, 6 gives 5. And 0, 6 gives 6. So, okay, it's a graceful labeling. But as far as complete graphs go, you cannot have a graceful labeling of a complete graph greater than with more than 4 vertices. This is a labeling of a complete graph with 5 vertices, but it is not a graceful labeling. It is the weaker labeling. In fact, it's the labeling, it's the weakest labeling, which is called a raw labeling. But those of you who have dealt with some combinatorial structures recognize that this is nothing else than these labelings of complete graphs is nothing else than planar difference sets, well known from geometry, and they give rise to projective planes, cyclic projective planes. So, in a sense, you can look at the row labelings of trees or graphs other than complete graphs as a relaxation or extension of the concept of difference sets. Okay, there have been results, papers in literature that publish results on the existence of graceful labellings. For instance, here is an example of a graceful labelling of a cycle with 8 vertices and 8 edges. And cycles can be labeled gracefully as long as the number of vertices is congruent to 0 or 1, 0 or 3 modulo 4, which means that the number of vertices is divisible by 4 or gives a remainder of 3 when divided by 4. When the number of vertices or edges in the cycle is 1 or 2 modulo 4, you cannot have a graceful labeling. This is a special case of a more general result, more general non-existence result. There are not too many non-existence results for graceful labelings, but there is one of them, namely that if you have an Eulerian graph with number of edges 1 or 2 modulo 4, then you cannot label them gracefully. An Eulerian graph is one that you can draw on a blackboard or on a piece of paper with, like in those puzzles that you have to draw a picture without removing pencil from the paper with one fell swoop, right? So, another paper by, actually this is by a famous mathematician, Roberto Frucht, and his co-author, Joe Gallian, where they proved that the wheels, and what is a wheel? I'm not defining it, the picture says it, what is a wheel? We have a cycle, and then we have a vertex in the middle, which is joined to all the vertices on the rim. So that's a wheel, and wheels always have a graceful labeling. But this is just a bit aside. Here is an example. Here's a picture of a typical lobster. So we have seen that the paths have graceful labeling, even alpha labeling. Caterpillars have a graceful labeling, even alpha labeling. Do lobsters have a graceful labeling? It remains unproved. Of course, the conjecture says that every tree has a graceful labeling. I'm coming to that. But so lobsters certainly are trees, but this remains unproved in general. So there's some difficulty there. So soon after Ringel proposed this problem, or conjecture, there were further conjectures. Well, actually, I'm mentioning 3 conjectures here. Kotzik's conjecture is the same as Ringel's, except he added the word cyclically, which means that you can decompose. Not only can you decompose the complete graph into trees, complete graph with 2n plus 1 vertices into 2n plus 1 trees with n edges, each isomorphic, but you can do it cyclically. So, for instance, let's look at this tree. I don't know whether it's visible very much here, but is it visible? Okay. So here is a tree, and here is some labeling of it. Okay. Now, what kind of a labeling is this? Well, if you look strictly at the labels of edges, so here the difference is 1, here it is 3, here it is 4, but here it is 7. But there are 4 edges. 2 times 4 plus 1 is 9. So we are working modulo 9. And 7 is the same as 9 minus 7, which is 2. and let's look at it why. This is the same tree with the same labeling, but drawn in a cycle which starts with 0, a cycle of 9 elements. It's the same tree, 0, 1, 1, 4, 1, 5, 0, 7. And we can see that 0, 7, even though it has value 7, the length of this edge is 2. The length of this edge is 2, length of this edge is 1, so these labels represent lengths of edges. And now, why does this yield a decomposition? Why does it yield decomposition? So let's take this tree and start rotating it. If I rotate this graph, the lengths of the edges don't change, right? This edge becomes this edge, 1, 2. This edge 1, 4 becomes 2, 5, and so on. They don't change the lengths of edges. So this tree, when I start rotating, it will never overlap with another tree and gives the decomposition. Okay, so that's the idea behind labellings, yielding cyclic decompositions. So Kotzik's conjecture, somewhat stronger thing than Ringel, that you have a cyclic decomposition. Probably Ringel had exactly the same in mind, but this is not how he formulated it. He must have had the same idea when you think about it. Incidentally, Gerhard Ringel, there was a German mathematician who was actually from Czechoslovakia, from the Sudetenland. And he worked in Berlin at first, but spent most of his career at University of California, Santa Cruz. And he was born in 1919 and died, I think, 2008. Finally, we have the weakest of these conjectures, the row labeling conjecture. Every tree has a row labeling. Row labeling is the weakest possible labeling. This is, for instance, a row labeling that I had. So there is hierarchy not only of the labelings, but also of the conjectures. Now, I alluded already to this. The complete, at least to one direction of this theorem, but the theorem says the complete graph can be cyclically decomposed into 2n plus 1. It doesn't have to be trees. The theorem works for any graphs. Isomorphic to a graph G with n edges, if and only if G has a row labeling. The if part is obvious, well, pretty much obvious, but it's not only sufficient, it's also necessary that you have this row labeling for a cyclic decomposition. So we have a hierarchy again, hierarchy of conjectures. So graceful tree conjecture implies Kotzik's conjecture, because if you have a graceful labeling, you have a cyclic decomposition. But cyclic decomposition is equivalent by this theorem to existence of a row labeling, which in turn implies Ringel's conjecture, which he probably had this kind of a conjecture in mind anyway. Now, there are many papers on labelings, not only this kind. Joe Gallian keeps a dynamic survey of labelings in electronic journals Journal of Combinatorics, and dynamic survey means he periodically updates it. But he deals also with other labelings, like magic labelings and all kinds of other labelings, which I'm not talking about. But even for the kind of labelings that I mentioned, there are several hundred papers already in existence. And they deal with one or another aspect. Now, I say the last update is from November 2011, but I think there might be a newer one. I just wasn't sure, and I forgot to check, frankly. But there may be a newer update. And that's a very good source of knowledge on the status of labelings, existence of labelings. There exist even at least 2 books on this type of labelings. One is by Ivashka and Javier, which is entitled Vertex Labelings of Simple Graphs, and appeared a couple of years ago published by Helderman Verlag. And there's another book by Susana Lopez and Francesc Muntaner-Battle, which is to appear, and I haven't seen it, only some sample chapters. There may be others. There are some volumes of articles on labelings, various kinds of labelings. I'm not mentioning this. So what are the most important results to date on the labelings and on Ringel's conjecture? First of all, everybody that I know believes that all these conjectures are true, okay? But as of today, the status of each of them, how things stand today, and it's not the same. For instance, it has been proved that every tree whose diameter is less than or equal to 5, longest path that you can find in the tree, if it's less than or equal 5, then it has a graceful labeling. So that's the status for graceful labelings. But for Ringel's conjecture, this implies, by a certain result, which I'll mention in a second, that every tree with the diameter up to 7, for every tree with diameter up to 7, it is true that there exists a decomposition that Ringel required. And the result that guarantees that is the following. If you have, suppose you have a tree T, and you remove all the end vertices and the edges incident with these end vertices, and you get another tree, say X. If X has a graceful labeling, then that original tree T has a sigma labeling. And so if you have a tree with diameter 7 and you remove the end edges, you get the tree of diameter 5, and that has a graceful labeling. Therefore, the tree of diameter 7 has a sigma labeling, but that's all enough to guarantee the answer to Ringel's conjecture positive answer to Ringel's conjecture. Or say, it has been verified by a computer that was done by Tank Aldred. He's called Tank, but actually his name is Robert E. Lee Aldred. And Brendan Mackay, that every tree with up to 27 vertices has a graceful labeling. So that's where it stands. But we can claim that every tree with up to 55 vertices has the property that there exists a decomposition into copies of this tree as Ringel required. Excuse me. So there's many examples like that. But this result that I mentioned actually also shows the difficulty. There's no good induction that one could use, or nobody came up with any good induction that one could use to prove truth of these conjectures. You make one step from a graceful tree to a tree which has a weaker property, but then it stops. You can't go further. You can't repeat this. You can't make proper induction. All the results, I think it's fair to say that all the results that exist use some kind of a direct construction. Some are ingenious and good. There are product constructions. Certain products of trees can be defined. But mostly these are direct constructions. Another problem is that nobody came up with a way of using any result, any deeper mathematical theories, and there is deep mathematical results, whether in number theory, in group theory, or whatever, to apply to this problem. So what is needed is really a very some new idea, something which would cure this disease. I want to mention one result which, in my opinion, is probably the strongest of all that we have available to date. And that's a result of Kotzig. Now, it's easy to explain what his result is. Not the proof. The proof is not easy, but it's easy to explain what he did. Take any tree, okay? Take any tree and choose any edge. So here is your tree, and you chose an edge, one edge. And now start to build up a sequence of trees, infinite sequence of trees. The first element of that sequence would be the tree itself. The second would be you took that edge and subdivided, make it a path of length 2, subdivided edge. And then subdivide further. That will be now path of length 3, and so on. So you stretch that edge, okay, ad infinitum. So you get a sequence of trees, and Kotzig proved that in this sequence there are at most a finite number of trees which do not have the strongest labeling, the alpha labeling. So it's a very, very strong result. And I don't know of any example where this finite number of trees is bigger than 2. So it may possibly be true that once you stretch that edge once or maybe twice, you already get a tree with alpha labeling. So that's a very strong result. In a sense, it says that almost all trees have alpha labeling. But it's not true that all trees have alpha labeling. And has some connection to the next result, which is a little bit more complicated to state. Now, here we are looking for labelings which are not necessarily graceful or alpha labelings or even row labeling. We just have labelings which are bipartite. They respect the bipartition of a tree as a bipartite graph. So I mentioned there are white vertices, there are black vertices. So you have white vertices, black vertices, and edges between white and black vertices. And the labels on, say, white vertices are all smaller than the labels on black vertices. So white on the bottom, black on the top, okay? So this is a bipartite labeling. And as I say, these labelings need not be alpha labelings, but we can define something as alpha size. So it's a maximum size of, it's a maximum number of distinct labels, essentially, over all such labelings for this given tree. And it's proved that roughly the number of edges, the number of distinct labels that you get is between 5 7s and 5 6s. It cannot, in general, it's not bigger than 5 over 6. It's probably 5 over 6 is the right order there. Okay. So, yeah, I don't think I'll have enough time to talk about the other problem, although that problem is interesting too. So what is needed, as I said, is somebody should figure out a way how to apply some deep results from, I don't care, differential equations, anything, to, I don't know, is there anybody here whose favorite are differential equations? Yes. We need a way to find some some application of these deep results from theory of partial differential equations into on this problem. Well, I would have liked to tell you a little bit about the other problem, which is also interesting, but I think in the interest of winning your friendship, I'll stop now.
So actually I would suggest a strategy based on what Peter told us at the beginning, and maybe you should tell them you'll write down a counterexample by hand in the next week.
Oh, okay. Yeah, yeah. That's the other suggestion I didn't make. Yeah.
Any questions or comments?
Does the statement of your original problem start with an existential or a universal quantifier over trees?
Just universal.
Okay.
Yeah.
All right. So you're supposed to be able to do this rotation regardless of which tree you start with.
Yeah. Yeah, sure.
In the middle, you had an if and only if theorem that talked about instead of a tree decomposition, just into a general graph decomposition with the cyclic stuff.
Yes, it's general.
Are there any of the other results that you talked about today that talk about general graph decompositions rather than just trees?
Well, only I mentioned some classes of other graphs like cycles and wheels, and there are results on other classes. Say, complete bipartite graphs can always be labeled gracefully. Not a difficult result. Yes, there exist results on many classes of trees, many classes of graphs, I want to say, which have labellings, graceful labellings, but these are mostly constructive, direct constructive results. People invent classes sometimes just to show that they can be labeled, yeah.
James?
Once you have a decomposition, what can you do with it?
Oh, that's a good question. Well, the problem of decomposition in general is very important because you have a whole, and if you decompose it into small pieces, you can handle the small pieces always better than the whole, right? So that's the idea behind having a decomposition. There's a whole theory of graph decompositions, not only into isomorphic subgraphs, but all kinds of things, yeah.
James, did you have a question?
Oh,
in the row labellings and corresponding to the cyclic order and decomposition of subgraphs. So what are those graphs? Can you say what are those for subgraphs? Can you describe any patterns of what the subgraphs, what those are? Corresponding to row labeling.
Yeah, there are some recent attempts to concentrate on row labelings rather than on graceful labelings, because these are weaker and supposedly you can get them easier. I mentioned the hierarchy of 4 labelings. This is the old hierarchy from the 60s. In recent years, there were many other labelings invented which are perhaps weaker, say, than alpha labeling, but still achieve the same as alpha labeling. Okay, here is something I didn't mention. Why do we consider this stronger labeling, alpha labeling? Because if you have a graceful labeling, you can decompose the complete graph with 2n plus 1 vertices into copies of a tree or graph with n edges. When you have alpha labeling, you can decompose the complete graph with 2kn plus 1 vertices, where k is any natural number, into the same thing. So alpha labeling, if you have an alpha labeling, you achieve much more. There are some weaker labelings defined, something between alpha and graceful maybe, or something like that, which achieve still the stronger decomposition result. But I have to say the labelings themselves do not settle the decomposition problems, because you have other congruence classes which then the congruent class 1 modulo 2n, when n is the number of edges, for which decomposition is possible. You can, take the complete graph of 9 vertices. You can decompose it into 6 cycles, for instance, right? But no labeling would produce such a decomposition. That's because 9 is not 1 modulo 12, right? So I do not want to give an impression that this is absolutely encompasses all the decompositions into isomorphic graphs, but it's a large chunk of it, and that was the original Ringel's intention to deal with such a decomposition.